for Government Network workshop, which will be running on Earth observation for water, specifically water quality applications. I'll introduce our other speakers as we get through things today. But just a reminder, if you could just keep your microphones off. If you want to have your cameras on, it's absolutely fine. If you do have questions during the talks, please type them into the chat window, and we are recording. So I'm just going to share my screen. Okay, so this is going to be a workshop looking at water-related Earth observation applications, specifically on water quality. Before we start, I do want to acknowledge the traditional owners of the land, and particularly the waters on which we meet and work. Pay our respect to their elders, past and present, acknowledge their current generation, and that organisations like Earth Observation Australia are working with these groups to build on their knowledge and understanding for managing and looking after our environments. So just a few more housekeeping tips just to begin with. If you do have challenges with the audio or the visual side of things, please type into the chat window and we'll try and respond to that. If for whatever reason the link drops out, we'll try and get back on as soon as possible. We are recording this today, so anything you say and do and we say and do is recorded. That also applies to the chat window discussions, both open and private discussions as well. All the material that we see today will also be on the Earth Observation for Government Network website. So those are the main housekeeping items to begin with. I do want to acknowledge the support for this activity from the sponsors down the bottom, particularly Geoscience Australia and the Digital Earth Australia program, and also Earth Observation Australia at the University of Queensland, and also to acknowledge Larissa Malpan, who's worked to get us all organised to put all of this together today. So just in terms of aims and outcomes for today, and also there's a subsequent discussion on Thursday. This is meant to be a set of discussion, knowledge generation activities, so that we can understand what extent of work's being done across research to, let's call it, operational applications, particularly in using satellite Earth observation products for delivering information about water quality. And it's also to move forward to how do we work together more effectively across a range of different sectors in doing research, delivering that as operational activities for government and industry across Australia. We acknowledge there's a range of programs going on already, and we'll come back to that in a minute. So what we're trying to get as outcomes from these activities, and this is, I think, germane to Earth Observation for Government Network, is we're trying to understand the extent of what's going on in terms of this particular, let's call it, applications area, try to record that and use it to help develop a set of coordinated activities going forward. So we're not taking ownership of that entire activity, but we're starting the discussion on it as well. So that's the aims, and then the outcomes for today and also Thursday's session. So a little bit about Earth Observation for Government Network, as I know a number of you haven't come across what we actually do in this area. What we're trying to do is get a sense of who's doing what and where in terms of those different activities that are in red across the top of the screen there. So going from areas where we're having research being done, that could be universities, research institutions, private companies, government agencies. Research isn't confined to universities. And how are those activities going from someone developing and testing something to making sure it works, to then delivering it in an operational context, whether that's for a government agency, a private company, or a non-government group. There's no one definition of operational. It differs for different activities. And then at the far end of that, we've got what we're calling operational national capabilities and applications by sort of foreign entities as well. The other way of looking at this, those of you that are coming in from more on the, I guess, the upstream or the space hardware development side is on the right there. So we're particularly interested in cutting across all these different areas in terms of what's being done with Earth observation. And today, it's about water quality applications. So what's happening in research infrastructure, private industry to government. So Earth observation for government networks' role in green is to sit across there. Space agency is meant to help understand what we're doing in those areas there as well. So this is essentially what EOGN does in terms of the journey that we've been on since 2019. And it was established to look at how do we pull together these research to operation areas for Earth observation. There are a number of priorities. You can see that water is one of the priorities that was identified in August 2019. And since that time, we've run a number of workshops, particularly across vegetation, land cover, land use and crop mapping. And we've moved into water. We did oceanic at the end of last year. And so this is moving into water quality and do water quantity later on. And all these sessions follow a similar approach to try and understand what people are doing and pull it together. One point I do want to mention in relation to this activity here is that some of you have contributed already into something called the AquaWatch program, which is a mission that CSIRO and SmartSat are looking at developing and delivering for Australia. That's a potential future source of Earth observation data. This activity isn't just about that, it's about where AquaWatch sits in the broader stream of data sources, knowledge and provision that government agencies and others use for monitoring and managing water quality. So if you've come across AquaWatch before, it's part of this activity. Earth observation in Australia has got a lot of different groups in it, and that's why we need to have discussions like this to determine who needs this information, who's doing work on it, and how does it fit together. We're never going to cover all of the different areas, but this is another approach to try and get across those and pull things together in water quality. There's a lot of work going on already, and we're planning to go in different directions. So this is where can we actually take it as well. There's just another view of the same set of activities, if you want, and the role of the space agency in it. So the point of that is, if we've missed something out, sorry, we'll try and include it, but we may not include everyone, and it is complex. Briefly, just SmartSat, I want to mention this because of the AquaWatch mission, which some of you have come up against so far. As I said, it's part of this activity. SmartSat has 3 programs. One of the programs is about Earth observation. And I just want to explain where AquaWatch sits in that research program. The CRC will have 3 main missions, which we will collaborate with partners on. And AquaWatch is one of those missions that it's developing basically over the next 5+ years. And as I said before, it will be one of the potential sources of data and information for looking at water quality. So when we do talk about SmartSat, that's why it's been given a sort of a prominent role here. Okay, today. So this is an overview discussion. I've gotten to the end of my overview a bit longer than I wanted to. So today we're going to talk about who's doing what. there is an online survey and discussion we'll come to. And in Thursday, we'll look at how do we put all of these things forward to start moving forward together and to act collaboratively in this space across a range of different government, industry and research sectors. So there'll be a summary report which says, here's what we identified and here are potential ways forward for the community to act on. Having done all of that, and a little bit over time, so we've just done the first 3 items, I'm going to jump into our next presentation. I'll just introduce our presenters briefly. So we've got Stephen Sagar and Janet Anstee. Stephen's from Geoscience Australia and Janet from CSIRO. They're going to be talking about some Commonwealth Government activities. Arnold Dekker from SatDek is then going to talk about the AquaWatch mission, which I mentioned briefly before. Magnus Wettle from EOMAP Australia is then going to present about the private sector. And you'll see after each of those presentations, we do have time for discussion and review, and then at the end, we'll pull it together. So I'm going to stop there and stop sharing my screen and pass over to Janet and Stephen for their presentation. Okay, I think one of you, not sure which one of you is unmuted. There we go.
So, I don't know.
Sorry, Stuart, can anyone hear us on that side? We're having a bit of trouble.
Yeah, that's great, Stephen.
That's about time. Apologies, we've made the cardinal sins of sharing computers in the same room, so we're trying to sort of shuffle backwards and forwards. Look, I'll get going because we're over time. I guess the major thing here for us, and Stuart touched on this, is there's many different types of flavours or operational workflows. So from a Commonwealth Government perspective, we wanted to sort of start the conversation here around what people in these audiences, and particularly on Thursday, what they would consider to be, the operational requirements around different water quality systems. And so in this first slide, I just sort of wanted to touch on some of the things that people generally consider when they talk about moving from what we've all traditionally done in EO and water quality in terms of moving from single scene analysis. So talking about timeliness of data, this is all in the context of looking to underpin monitoring and those kind of things. Talking about validation and calibration, what kind of infrastructure and processes need in place for assurance of quality of products, robust infrastructure, things like storage and compute, reliability. So how do you actually manage when you've got an operational system up? How do you actually manage downtime? Things like that, especially if it's been built into a workflow for people to do monitoring applications. And of course, automation. So this is the real key one that sort of moves us away from that hand cranking and tweaking of different individual sites or monitoring things. And we wanted to really think about in our Commonwealth projects, and I'm going to be talking a little bit about the framework we've considered. Janet, can you move to next? Where are we on here?
Yeah. Go arrow down.
I don't have any. There we go. Yeah, we're back on. So we gave a bit of thought when we've been establishing these projects around a generic framework for what we need to try and tackle in terms of operational water quality flows. Now, these are kind of things that have been highlighted in past years. I know Arnold was involved in a gap analysis, looking at what needed to be tackled for operational type analysis. Looking at that top row up here, we've got all of our data inputs. So talking about the EO data itself, and it's something we'll go back to on Aquatic ARD. We've got things like citizen science projects, which are starting to play a bigger role and adding value across different kinds of projects. We've got what we're calling biooptical characterization on the right. I guess that's a proxy for many people in this room for fieldwork, lab analysis, and filling in the blanks and really enabling different types of analytical algorithms to be implemented. Through the middle stream there, you've got your program, your platform and delivery. So these kind of things from a government perspective, from Geoscience Australia especially, we've got things like Digital Earth Australia, but there's flexibility in that for private industry in terms of AWS and those kind of platforms. And then at the bottom, I guess what we're calling extra add-ons or collaborative efforts. And these things are where other agencies come into play, other kinds of area of science, and how do we integrate them back into the process chain. So there's the whole CalVal exercises, which you obviously need contributions from state government agencies and different kind of inputs from places like Bureau of Meteorology in terms of meteorological outputs. And how do we have that back and forth between the different value-add processes from different areas of science? Now, Janet's going to show how our current projects are actually touching off on many of these aspects. But I was just going to firstly focus, I guess, on the traditional blockers. So these are the things that we've identified in the past that have been a real hurdle for many of these agencies to try and get through to actually move to an operational framework. So aquatic analysis ready data, essentially this is EO data that's had all of the processing done to it. So you've got atmospheric correction, you've got things like masking and QA/QC. That's reasonably mature for terrestrial applications, but very much still an experimental work in progress for aquatic. Even the USGS has started to just move to their provisional product. These things have issues in land water. We don't really have a way forward to do this operationally. And this is a place where private industry can also help, because these are things we're trying to build ourselves and we don't often have a way to move forward on these things. So looking at the characterization, things like fieldwork, looking at biooptical optical properties of water bodies. Now, a lot of this fieldwork really underpins how successful some of these algorithms can be. Often we work in these sort of one study area, one image frameworks where we can sort of hit something over the head with a hammer. And Heron Island, people have spent decades up there getting fieldwork, characterizing these areas, but extending this out into something that we want to do operationally without having to tweak, something we want to do at a continental scale, enables a bit of smart thinking about how we can actually invest in this field work and lab work to try and get these biooptical databases ready so we can run these analytical algorithms at scale. And of course, platform and delivery. And obviously this is where myself and Geoscience Australia, this is sort of where we play the biggest role. And we're looking at that from a digital earth perspective, but there's other ways of looking at this. Obviously people are doing things on the NCI, Amazon Web Services is starting to become a bigger platform that people use. It's not only just the storage and the compute, but you're looking at things like pipelines and how you deliver the data successfully for an operational product. Traditionally, these three kind of areas have really been a bit of a blocking point for spinning up operational projects, but we're starting to address these things. So I guess this kind of workshop is quite timely for us at the moment to see how we address these going forward, talk about them, and Janet's now going to talk a little bit about some of the projects we have in train and how they sort of touch off on some of these other aspects.
Thanks, Steve. Can someone see that? Thanks, Steve. So I'm just going to talk a bit about how the operational framework fits within our current work. And I've got 3 case studies to demonstrate this. The first project is a collaborative project between Geoscience Australia and CSIRO. And the aim there is really to develop an operational capability to monitor inland water quality using Earth observation. And some of the expected outputs of the project are listed there in the table at the bottom left. The activities undertaken so far include biooptical characterization, calibration validation, and ancillary data collection. And of course, algorithm implementation and product development on the platform. And in this project's case, the platform is Digital Earth Australia. So the activities undertaken so far include a gap analysis, a biooptical gap analysis of the historical data sets. And then we've undertaken acquisitions of in situ data in the gaps that we've identified. We've also managed to select a range of match-up data with in situ observations that coincide with the satellite overpasses for validation efforts. We've integrated the citizen science observations. We've built up a parameterization for a continental scale physics-based algorithm. So the second case study is the Prime Water project, which is a European Commission Horizon 2020 international cooperation funded project, which aims to deliver predictive tools for water quality assessment using Earth observation and hydroecological modelling. There's 10 partner organisations and agencies, and CSIRO, Melbourne Water and SatDek are the 3 Australian ones, although EOMAP is also one of the international collaborators. The activities that we are undertaking as part of the Prime Water project include biooptical characterization, calibration and validation, ancillary data, which also includes input from end user communities and stakeholders. Value add, we're doing some hydrodynamic modelling with our CSIRO land and water colleagues, and of course algorithm development and water quality product delivery. The project has 6 work packages, and we're somewhat involved in all 6 of those work packages, but the project itself has 4 study sites in which they're focusing these activities. 2 are overseas, one's in Italy and one's in the US, and Australia has 2 study sites. One's at Melbourne Water wastewater treatment plant, and the other one is our long-term site at Lake Hume. We're also working with time series of multispectral data with Landsat and Sentinel-2, but we're developing products for the hyperspectral data acquired from the PRISMA and DESIS satellites. And we're also working with the project in terms of putting together a virtual laboratory, which will enable stakeholders to test data from EO sensors, models, and also forecasting tools. The third and last test case study case is the Citizen Science Project Iron Water Australia, which commenced in 2017. And it really was designed in order to help us fill in our gaps in knowledge, particularly in the remote locations throughout Australia. And we're hoping to use this data to help calibrate satellite imagery as part of an integrated program that uses in situ laboratory as well as citizen science data to calibrate. The tasks in this project include engagement with groups and communities in bringing them into the project through outreach and education, and also demonstrating to them how their observations can actually be incorporated into the science, in this case, the calibration and validation activities. We also include physical and chemical data products that our citizen scientists collect. And of course, we then compare the data with the watercolour products from the DEA. The watercolour observation data is delivered to users and other interested people on the project website. and an example of this is seen on the left-hand side. And we also undertake statistical analysis of the data and provide that to the users so they can have understanding of the frequency of watercolour at their particular sites. This data can then be compared with watercolour data derived from satellite imagery. And on the right, got an example of ocean colour maps that's been produced by the Forel-Yule imagery. In our project's case, we're hoping to overlay the citizen science fire and water data onto the DEA produced inland water quality colour maps and do a comparison of that for this project. So the key benefits and learnings derived from this work have been using a variety of tools and methods from a range of different projects has enabled us to do this through consistent protocols and standards. We've really benefited from having access to open, publicly accessible data, and certainly made use of the efficiencies that ARD analysis ready data makes for us. And we've also identified the real benefits of having our own and other people's match-up data sets available for integrating into the project for understanding variance and accuracy. We've also really spent a fair bit of time in building up relational databases so that all the information and knowledge we're obtaining from our current and historical data sets can get transferred to other projects going forward. And we've been relatively successful in keeping the science developing for emerging satellite sensors, such as the hyperspectral data that's coming on board. We've also found that this integrated approach that we've adopted using a range of models and methods has actually given us the best opportunity to develop this continental scale product. And finally, we've just really found that given the confusion of the different projects that are out there in the community, the importance of strong and clear communication, demonstrating the linkages between these projects to stakeholders and the wider EO community has been really important in order to reduce the confusion, but also to give us real opportunities for collaboration going forward. Thanks.
Excellent. Thanks very much, Janet and Steve. And apologies again just for the audio challenges at the start there. We do have a number of minutes left for questions. And so if people do have questions, please feel free to type them into the chat window. Given that we've got a decent number of people online today, we'll work through them in the chat window in turn. So just while people are doing that, Janet, that last point you raised about communications is a really important one, and something that we've seen in other EOGN workshops in terms of within the community who are taking the data and turning it into usable information, but also working with the groups who use that as well. How, I mean, are there lessons as well for what's the best way to approach doing that? Because that's a, you know, that's a lot of activity and a lot of people to talk with.
Yeah, indeed. I think that's why we're reliant on coordinating groups like EOA, I guess, in order to really articulate the current work packages that are going on in the community.
Yeah.
But, you know, I think we're missing a national seminar series or at least a conference series that we used to have in the Australasian remote sensing community. So we lose a lot of communication. So it's quite difficult to do that in a comprehensive way. But we do need to ensure that the public accessibility of the data that we're making available to the community can be searchable. And it's really interesting. We've been thinking about different mechanisms for sharing out, for example, our bio-optical database. We have a mechanism in CSIRO called the Data Access Portal. So this is a mechanism that is quite useful, but is it searchable and fit for purpose for the EO community? These are conversations that I think we could have and be used to actually extend that those data sets.
Well, thanks, Janet. I'm going to be really indulgent before I answer those other questions. Just quickly, National Forum. Right. We didn't pay Janet to make that point. I think a lot of you know we are running a national forum. Last week we just announced it won't be face-to-face this year, but it will be online in August. We'll be running a series of community webinars every 2 months after that to build that continuity as well. So I'll stop doing that. You'll see more information about that later on. Just going back to the questions. The first question there from Manish, is there any case study of the use of deep learning for water quality mapping? So are people using AI and machine learning?
Yeah, well, I can answer that one. A collaborator of ours in the Prime Water Project has, which is Nima Pavalan. He has just published a deep learning example of water quality using a range of different data sources. So he is currently using the same sort of methods to test the retrieval of phycocyanin, the pigment that's found in cyanobacteria, for Prisma data. So yes, these techniques are developing, and I guess that's what I meant by we are continuing the science for emerging technologies.
Thanks, Janet. And that is, again, another reason for these sort of discussions is to, we want to know what people are doing with the data and the processing techniques. Next question from Guy. Does Eye on the Water accept RGB imagery from point photos or transects from drones?
Yeah, thanks, Guy. Yes, no, it doesn't at the moment, but it's one of those interesting things that we started thinking about because we wanted to actually have a look at how good the algorithm within the application processes the Forel-Yule colour scale. So we started taking photographs and then converting that to the Forel-Yule scale in comparison to the one that's uploaded to the website. And so we know we can actually produce a Forel-Yule from an RGB photo. So we can indeed do that for the drone imagery as well. But at the moment, it's not operational for the application. But what we could do is look at an integration of that drone data in the same way that we're looking at integrating in situ or other laboratory measurements into the process.
Right.
Stephen.
Thanks, Janet. And there's a last question from Benoit, and then we'll move on to Arnold's presentation. There's a question for Steve. It said you introduced automation to reduce human interaction in the operational systems. I'm used to see more labour going into operational systems while still automation is a prerequisite to operational. I don't think of any example. There's no significant background labour and significantly more than non-operational systems. I'll take that as a point, not a question. You're safe, Steve. All right, last one from Gia and Lee. How do you integrate feedback to satellite imagery providers or the algorithm developers if you come up with different water colours or data during your in situ measurements?
Yeah, I can take that one if you. Look, I think that's one of the biggest challenges we have. Sorry, we're unplugging here. One of the biggest challenges we have is if we've of doing these matchups and we're getting different sort of comparisons through iron water data or different algorithm retrievals as compared to the different, I guess, I'm assuming you're meaning when we're doing this validation, it's feeding it back into our processes. So I mean, right through that value chain of ARD through to algorithm results, it's really challenging to tease out where those matchup difficulties come from. And I guess it's also an issue talking about in situ validation data and considering that as truthers too, in terms of uncertainties in the in situ validation. So this is all something in GA as well as part of the DA program, is we're really starting to sort of tease out what our accuracies and our confidence is in our validation data through our CalVal efforts, and trying to tie them down to assessing the quality in our ARD and how that flows through to algorithm retrievals. Honestly, it is a challenge. So working out where those error budgets sit and, how much you can trust that data, it's one of the biggest challenges we have.
Thanks, Steve. That's a really good point. And again, for our other sort of discussions of other national products, that loop or that feedback between on-ground measurements and algorithms, and products is really important. So that was a good set of questions. Thanks again, Janet and Steve. That was excellent. And we will be making presentations available to people afterwards if you want to look in more detail. All right. I will now hand over to Arnold Dekker from SatDek to talk about the Aquawatch mission. Arnold, hopefully you're there and you can share your screen.
So I'm here.
Perfect.
Can you hear me? Can you see the screen now?
Perfect. Thanks, Arnold. Looking good.
Good. Thank you. So the Aquawatch Australia mission is about the future and about innovation. It does fit quite nicely with what Janet Anstee and Stephen Sagar presented. This mission, funded at the moment by CSIRO and the Smart Satellite Collaborative Research Centre, is very much looking at the future of remote sensing and water quality. So it has an ambitious goal to have a comprehensive national water quality monitoring system by 2026. And it's very much about the integration of in situ sensors, modeling, data analytics, as well as the sensor technology from aircraft or in space. This is a concept diagram. This is definitely not what it's going to be like, but we had to draw up something of the ideas we have with possibly 2 dedicated satellites that will be actually global satellites, but they will be designed to address the Australian ecosystems. But it's very much a matter of trying to increase the in situ sensor data capacity in Australia, but also the integration of the data into water quality modeling and with low altitude, high altitude and spaceborne platforms. So it's quite a challenging and interesting mission. Now, these are the challenges, some of the challenges in inland water quality and in coastal waters, as well as coral reefs. And of course, an industry dependent on that, which is aquaculture. And it's also important for Australia meeting their targets in the Sustainable Development Goals and being able to report, as in the top right. The initial partners and collaborators are given on this screen. As you see, they are universities, but also consulting companies, Water Research Australia, and several government agencies, including Defence, as well as the Australian Space Agency. And that's actually, those partners are the current partners. More partners are welcome. So the aim is to improve management of our aquatic ecosystems and help related industry growth. And industry growth is important for both CSIRO and SmartSat CRC, because that has to be the ultimate, one of the ultimate achievements of this mission. So the focus is on inland water, coastal water, as well as our optically shallow systems such as seagrasses, macroalgae, macrophytes in inland waters, coral reefs, etc. And there's definitely a focus on potential harmful algal blooms and specifically cyanobacteria. So we have our inland waterways in Australia, which are not easy from Earth observation. The large lakes are easier, but when you get into these kind of systems, as on this slide, it becomes a lot more difficult. And you need finer spatial resolution. Our coastal waters and habitats are complex as well. They fringe on the land, so you've got the land-sea boundary. But we all know that Australia is also a maritime nation, where our sea area is multiple times our continental area. And we have to manage that as well. So we're also in the process of drawing up specifications and beginning the process of designing Australian Earth observation satellite technology. But as I said before, it's not only satellite remote sensing, it's the coupling with sophisticated or cheaper or better integrated in situ sensors, coupling it to three-dimensional water quality flow models, similar to what Janet Anstee presented for the Prime Water project in Europe. And the AquaWatch mission will support the growth of the sensor and space technology area in Australia. The aim of the Australian Space Agency is to create 30,000 jobs by 2030 and a $3 billion space industry. And this is definitely part of that aim. So again, it's about integration of in situ data, water quality modeling data, just above water data, drone data, high altitude platform data, and Earth observation data. The water quality products that are currently possible were already discussed by Janet and Stephen. They are the water column optically active components like chlorophyll and the cyanobacterial pigments, total suspended matter, color dissolved organic matter. Once you know those, you can actually estimate the optical conditions of the water as well as the bathymetry. And we have some experimental data here, which was done by Janet Anstee's group on using WillView 2 data, commercial data for Lake Burley Griffin in Australia. In the future, we think we can work on phytoplankton functional types, on sources of color dissolved organic matter, not just the color dissolved organic matter, but distinguishing freshwater from estuarine from ocean dissolved organic matter, particle size distributions, and possibly diffraction of inorganic to organic matter. And together with what's currently possible, we can look at all these issues in the lower squares, which is what water management really is about. So, of course, people say, yes, but how will AquaWatch, how will, in this case, the satellites, will be different to what we already have, which is Landsat and Sentinel-2 from the European Space Agency. Landsat is owned by the United States Geological Survey. Basically, on this graph I'm showing you here, on the right-hand side, you've got turbidity, Secchi disk, vertical attenuation light, and suspended matter. They can be done with most sensors that is developed for land remote sensing, such as Landsat and Sentinel-2. They were not designed for water quality. As you go to color dissolved organic matter, to your chlorophyll, to your cyanobacterial pigments, and maybe particle size distributions and fractions of organic to inorganic matter and shallow waters with bottom visibility, you want more and more spectral bands, and you want better and better spatial resolution. And we think that's where AquaWatch can play a role. We also think that AquaWatch should be designed in such a way that it's complementary to these massive programs that involve billions of dollars for Landsat and Sentinel-2. Here's an example of the in situ sensor deployments and the kind of online dashboards that we anticipate going forward. And Janet and Stephen have also shown examples of this. The water quality modeling and assimilation of remote sensing data and in situ data is something we feel has a strong and bright future, but needs significant investment in capacity in Australia. Because you want to use the satellite data and the modeling data in order to be able to measure accurately what's there, but also be able to predict many days in advance. From our end user workshops we did for AquaWatch 7 in the last 6 months, increasing the prediction period from 1 or 2 or 3 days to 7 days and increasing the accuracy was one of the most important end user outcomes in the long term. So what are we doing in AquaWatch? Well, we are in phase 0, as we call it in space agency speak, which is where we've been conceptualizing, we've been doing initial research, we've been looking at the end user requirements, we're doing some initial studies of what satellites would look like. But we are now in the process of developing the program for the next 2 to 3 years, because base funding is available from CSIRO and the SmartSat CRC. We're thinking of pathfinders, which are bigger than CubeSat satellites, let's say suitcase-sized satellites, that can look at some of the aspects that we will want in the ultimate AquaWatch, such as, for instance, focusing on blue-green algae and being able to measure the pigments really accurately. On the other end, maybe a joint defense civilian program that's around hyperspectral remote sensing and onboard programming and pointability, etc. So we are in the process of building new partnerships, needing to prove the science, technology, and applications. We'll also still be developing some of this. And some pilot projects are now being considered around Lake Hume, which is also in the Prime Water project, but also Lake Tuggeranong in the ACT, Coburn Sound in West Australia, where some major port developments are planned, Moreton Bay in Queensland, aquaculture in South Australia, and there are more pilot projects in development. The purpose of these pilot projects is to demonstrate what we can do now, and also to involve the end users in understanding the potential, so that they can start thinking what needs to be done in the future. This is our preliminary mission implementation schedule. So we're thinking about launching the actual AquaWatch satellites from 2026 to 2027 onwards, because that's how long it takes to actually go from funding through to a satellite being in a complicated, sophisticated satellite being in the sky. The funding is not secured, so business cases are being made at the moment to start that process. But as you see, there's launch and operations, there's instruments, the in situ sensor network, the satellite bus and integration, and ground data and analytics system. So this will all have to be developed, and we will have to make sure that we can do that in Australia, or that we collaborate with international partners where we don't have enough knowledge in Australia. So this is the final slide, which shows where the pilot projects sit in the different states, addressing different issues. You also see in light gray are some experimental sensors, such as the DLR DSIS, which is on the International Space Station, which is an experimental imaging spectrometer that already is being used in Australia. We've got the Prisma hyperspectral satellite from the Italian Space Agency that Janet Anstee's group is working with. There's the Hisui from the Japanese space research organization, also on the International Space Station. So we have some precursors. We want to build these pathfinders to develop the capability to be able to build the big AquaWatch satellites down the track. And we also think of collaborating with the Canadian Space Agency, with the French Space Agency, with NASA, with the European Space Agency, and many other space agencies as well. And that's the end of my presentation.
Well, thanks very much, Arnold. That covered a lot. And just putting things in context, with all of the workshops we have for Earth observation for government network, we usually do have quite a mix of people in terms of those who are taking the imagery and other data sets and turning it into information, those who are actually using that derived information in decision-making processes, and that these groups are not necessarily just in government, they're in NGOs and private industry as well. So it's quite broad. We're really happy that Arnold was able to present today, because the Aquawatch initiative is hopefully something that will pull us together nationally in terms of our science, government and industry capabilities to do and deliver capabilities that everyone can use. So I'll stop there and open it up to the floor for questions to Arnold about the Aquawatch mission. And keeping in mind that this is, there's a satellite component to the mission. There's a ground-based component that is meant to build on existing measurements of water quality parameters in a range of freshwater and coastal bodies as well, and to enable those to be put together. So we're not just talking about a satellite system. All right, first question's from Taufik. Arnold, how soon should we aim to reach out in terms of regarding the provision of payload and bus subsystems for the Pathfinder satellites for Aquawatch? And given that we've got a number of companies online today that are providing those capabilities.
Okay, I'll answer that question, but Benoit had a question before.
Oh, sorry. Yep.
I think, but that's okay. Well, doesn't have to be in sequence. So the process will be that the Pathfinder missions will need approximately $5 to $10 million of funding each. And that funding isn't there, so we have to make the business case for those Pathfinder funding. And only when the funding for those Pathfinders is secured, then there will be a process of probably going to tender for all the industry components that have to do with the Pathfinder missions. So that's the way the SmartSat CRC and CSIRO will run the Aquawatch mission.
So we're looking at, at least 1 to 2 years. I think as Arnold said, we're just getting towards the end of the phase 0 study, which is, here are the needs, here's what this ideally would look like. So a bit down the track. So just going back to Benoit's question, sorry I missed that before. How advanced is the satellite concept? Are there resolution in terms of spatial and spectral goals, requirements, types of orbits, those things? Over to you, Arnold.
Yeah, so we have done studies and workshops in the last few months, and basically we follow the recommendations from the CEOS report from 2018, which is about the feasibility for an Earth observing system for aquatic ecosystems, non-oceanic aquatic ecosystems. And those recommendations, we checked them and they still seem to be quite valid. So in short, probably we want covering at least 380 nanometers to 1,000 nanometers, possibly shortwave infrared. And the spectral resolution would be 8 nanometers. And the signal to noise would have to be as high as possible, given that the spatial resolution will probably be around 20 meters, is the current thinking. The problem with spatial resolution is if you go to higher spatial resolution, you reduce your repeat frequency, and higher spatial resolution also massively increases the size of the satellite and the cost of the satellite. But these are trade-offs we're still working on. We're actually proposing now work with the SmartSat CSC and CSIRO, involving UQ, CSIRO, Curtin University and Australian National University and my own company, to build an end-to-end simulator in order to be able to quickly calculate what the consequences are of increasing or decreasing scope of certain aspects of the satellite sensor technology. The orbit repetitivity, if you go for 20 meters, one satellite will have a maximum swath width of 400 kilometers. So the repeat frequency will be quite low. That's why we want to look at multiple satellites. But we're also thinking of, can we fly it in tandem with Sentinel-2 or Landsat, so we get complementarity between these satellites.
Well, thanks, Arnold. And I think one of the good aspects of Earth observation that we've seen again in our other workshops is this type of activity enables international collaboration. And this is something that we're quite mindful of in all of these areas and want to build on. And sort of leads a bit into Stephen Ward's question. So is AquaWatch seen as the genesis of some commercial data industry or as a public good data source? So I think the question's around data. In either case, where do we see the main competition, noting that there are many hyperspectral missions in planning stage at present?
So it's an excellent question, and it's one that we know about, we're thinking about it. There's no answer, because the answer will actually come from how we fund it. For instance, will venture capital fund it, or private companies fund it? Will NGOs fund it? Will the Australian government fund it through the Australian Space Agency? Will it be a collaboration of state agencies and the Commonwealth government? Will it be a collaboration, for instance, with the Canadian Space Agency, because they want to build a similar satellite. However, they want to make it 100-meter resolution, so it will have a high frequency. We could build the fine spatial resolution 10 or 20-meter sensor complementary to the Canadian watersat. So that's an option as well. There are many options. We are aware of most of them. Making those choices depends on how our business case that we are writing now within CSIRO and with the SmartSat CSC, how they are going to be received, and ultimately where the funding will come from. Because let's say if it's Commonwealth or state funding, it's highly likely that the data has to be publicly available. So if it's private industry, it may go down a different route. Those are the unknowns at the moment, and we would love feedback from everybody where they think this should go.
Thanks, Arnold. Just noting time and noting that Benoit's made a point we should take note of in relation to the former SAT orbit and timing approach. Thanks, Benoit. We'll note that as part of the output for this. Thanks very much, Arnold. Actually, that last point Arnold made in response to Stephen Ward's question is a good segue into Magnus Wettle's presentation, which is going to look at the private industry side of water quality. Just before Magnus talks, I do want to make the point that EOGN did start out as government network, but it's quite clear that if we're going to progress at local, state and national levels, we have to have more effective partnerships with private industry in terms of what we're doing. And we've been able to do that in other workshops. And this is definitely an area where we're looking forward to doing it as well. So we're really pleased that Magnus has got time to present today. Magnus, over to you.
Thank you, Stuart. Yes, so hello everyone, good afternoon. I'm the Managing Director of EOMAP Australia. And today I want to talk about, operational Earth observation, water quality monitoring, specifically for inland and coastal waters, but to give you the industry perspective as I see it. So briefly explain who we are, the principles behind what we work with water quality monitoring, and then some case studies to show how we deliver these as services. So we deliver water quality data as a service, but then move on to delivery platforms, and finally turnkey systems that enable others, third parties, to produce their own water quality data. So really, really briefly then, we map and monitor aquatic environments worldwide. That's what we do. 95% of our work is done using satellites, and really we either map in shallow water systems, we map the seafloor, the bathymetry, how deep the water is and what's on the seafloor, or we map what's in the water. So water quality monitoring. And what we bring to the mix is our algorithms, how we solve the radiative transfer problem, and how we have the processing system, the operational processing systems to apply these algorithms on large volumes of data. So we come from we're a spin-off from the German Aerospace Center originally, and the first and probably still leading commercial provider of satellite-derived bathymetry. And the point there is that that's actually the more difficult thing, in my opinion, to solve. But one of the things you need to solve to calculate bathymetry is what's in the water column. So that's how it's all connected. And what I want to mention is that we've been part of this now for aquatic remote sensing for 15 years in the industry, and we've really seen how the uptake, the use of water quality, of Earth observation water quality data is increasing, and it just keeps increasing. Not just the use, but the acceptance of it. So here's an outdated slide of some of our partners. So we do work with CSIRO and Geoscience Australia and University of Queensland, and a number of industry partners. So I think the previous talks perhaps haven't really talked about the mechanics, but I think that's not within the scope of this presentation, of how we derive these various environmental variables from the water column. I do want to mention how we do it within EOMAP. It's a physics-based approach where we have various databases of the atmosphere and the optical models, bioptical models, which were mentioned in the previous talks, and the sensors. And we apply a number of corrections, such as adjacency correction and so forth, before we even consider retrieving the water quality parameters. And the atmospheric correction being the critical point here. That needs to be done as part of this workflow system. And finally, there's the quality control aspect. The previous talks have already listed some of the environmental variables you can get from this technology. Would like to add sort of the more expanded version of all the ancillary data outputs and complementary data that comes out of a physics-based system that you can use to retrieve various environmental variables and everything that can be done. And finally, the quality control. So if your physics-based system is set up correctly, then you already know your geometry of your sensor and your viewing and your illumination. You know your aerosol optical thickness if you've done your atmospheric correction. All these variables can be essentially stored for each pixel that you solve for in an image, and you can create a quality coded image as seen here in the bottom right. This can be done automatically as part of the processing workflow and summed up to a total quality image. So that's all done as part of the processing workflow, but inevitably there will be a manual quality control at some stage. But the point being that this is also part of the workflow system. So that's a really quick run through of the principles behind how we work with water quality. And now I'll move on to some case studies, which are about water quality monitoring data being delivered as a service. So I guess I want to illustrate how industry is delivering this data and who is using it, who is paying for it. But first, I'll start with two continental scale projects. This is for the whole Mekong River system. It was 6 years of monitoring water quality using 3 different satellites across 6 countries. And there were third-party companies or partners in this project who had in situ monitoring stations validating the satellite-derived environmental variables, which were turbidity and suspended sediment. That was the main properties being solved for. So this was done in 2013, 2014, so a while ago. Here's another continental scale project that was done over 3 years for all the inland waters of Europe, for the European Union. And again, this was validated independently with in situ stations for many of the sites. So the point with these 2 projects is that, well, it was operational in the sense that within EOMAP, our algorithms were running this operationally. This was too much data to do manually, as Steve alluded to earlier. And it was also done quite a while ago, more than 6-7 years ago now, and independently validated. So I want to get the point across. This technology has been done at this scale at an operational level, is being done now for several years. And that brings me on to the topic of validation, which I'm not going to talk about in this talk, but I know that it's important, especially when industry is coming to the party and talking about technology with research agencies. So I know it's a bit anticlimactic, but we have a validation report on our websites you can download and look at. But just because I know that's not very exciting, I asked the water quality team if they could send through some recent slides on validation, and they sent through a PowerPoint with 110 slides of validation from all our projects. So essentially, it was just too overwhelming, and I'm just going to refer you to that if you email me or if you go to the report, because I think it's beyond the scope of this talk. And now I want to move on to a bit more specific projects, not the broad scale continental style. This was Nord Stream 2. For the longest subsea pipeline in the world. There was dredging involved in installing this. This is still ongoing. It's quite controversial, piping gas from Russia to Germany. But we monitored the turbidity or the effects of dredging for this using satellite remote sensing. That's one type of quite common industry application, is dredging monitoring. So I think it's important to keep in mind here how water quality data is used in industry and who's paying for it. If you're thinking about how to stimulate the space industry in Australia, you know, what can a small company do to provide water quality data services? Here's another one, completely different. This is harmful algal blooms in Florida. Again, this was validated with in situ stations for the local government, I think, or for the regional watershed authority. Here was drinking water reservoir monitoring for Greece and Italy, again with independent validation, where we provided chlorophyll, turbidity, temperature, and harmful algal bloom maps. Here is some validation data. So the black squares are the in situ data being matched up with the different sensors used in this project. Hydropower reservoir monitoring in Africa, again with independent validation ground truth data. And here the data was also delivered within our EOAP, which I'll talk about more. That's essentially a visualization platform for the Earth observation outputs. More validation data. And finally, bringing it closer to home, how this is being used in Australia in industry. So here we have the North Queensland Bulk Ports Corporation. They had two different ports where they were monitoring turbidity with benthic turbidity loggers and near real-time measurements, but they took the initiative that they should also use satellite data to have a more synoptic view, not just point measurements of turbidity, and brought us in. Well, it was Port and Coastal Solutions was the environmental consultant who brought us in on this project. So one was near the Great Barrier Reef. So for obvious reasons, they wanted to monitor turbidity there and see if it was diverging from background signals. And that's another point. One reason that industry will turn to remote sensing data is that they want to see what was the turbidity in the past. So you can use satellite archive imagery, not just sensors in near real time. And then for the Port Weipa, they were dredging again. There was a very extreme wet season with lots of sediment deposited, and they wanted to understand how much of this was natural variability and how much was coming from the actual dredging, since they have important compliance requirements. So that's a screen grab of that. The output annotated by Port and Coastal Solutions, and it's actually a screen grab from the EOAP software. So that kind of was a very quick run through of some of the ways that people are, some of the reasons or applications rather, why people are purchasing water quality data. So now I'll move on to what I considered the delivery platforms. I've alluded to the EOAP. This is something that we realized was important to have for a lot of clients. So a lot of clients don't actually want to be handed GeoTIFF files, and they have to open up ArcGIS and start color coding and interpreting the data. If they're given a login to a secure platform, online platform, an area, they can choose the environmental variables they have commissioned for that project. In a drop-down menu, they can choose the time interval. They can have a look. This is near real time, so it's updated as the satellite data comes in and is being processed automatically through the system. And they can even put a virtual station and bring up a time series of turbidity for that location. This is what a lot of users actually want. So almost just a qualitative, I mean, this is quantitative, but they're not actually interacting with the data as such. They're getting a bird's eye snapshot, almost qualitative view, but still reliable data, of course. So this is something I want to mention, that having this kind of data delivery we found is valuable for users. Here's an older version of the EO app that was used. UNESCO, they commissioned a pilot study as part of their World Water Quality Information Capacity Building Portal. So this is water quality, coastal and inland water quality for the entire globe. I think it's 6 months worth of data, downsampled to 90-meter resolution. So again, just visualizing the data, if you will, and you can go to the website and have a look. So that's visualizing data. You could deliver that really just as part of a service, but the next step is actually to enable third parties to create their own water quality data. So that's what we have here. We have essentially two ways to do this. Either you install it at the client on the client servers, a fully operational turnkey system, or you can offer it on the cloud. And that's what Eolytics is, our Earth Observation Analytics Suite. This is for water quality, runs online. You have a map, you choose a location, you can draw a square for the area you're interested in. It'll connect up to the satellite archives, such as European Space Agency Sentinel Archive, download the data directly to the cloud processor, so you don't have to download data to your own machine, and then simply process the images that come up as part of your search query for location and date range. And all you have to do is download the final outputs, the turbidity, for example. So this is a cloud-based way to enable, whether it's a small consultancy, to add water quality data as one of the things they can deliver as part of a more comprehensive delivery of other environmental information for their projects. But it can also be government agencies. And this is a client in Brazil. They had this running, and the photo there is the guy who was really excited that when it was first set up, he went to have lunch and launched some turbidity monitoring in Brazil from his phone. So I alluded to it earlier. This can also be set up. It's the full physics-based backend with the quality control and atmospheric correction as we use it ourselves to deliver our water quality data services. This can be installed locally on servers and then customized to output the type of information you want, whether to the EO app or to an agency's own version of how they want it. So essentially a turnkey water quality monitoring operational processing system and set up to process archives or to process in near real time. I don't have any screenshots of that because that's set up differently for each agency. We have it running for about half a dozen agencies at the moment. And finally, I guess you could sort of say it's a combination of all of this. Where we are at now is providing a water quality data visualization system, but that also includes the ability to process water quality data using the Eolytics system. So in the cloud, if you will, or on your local servers, if you have your own system, in near real time, but also to visualize, to bring in other data. So that's the EO portal. So it's similar to the EO app. You here have a water quality data that you've created, but you might have done it in real time because you can launch it from here. You can input also different data, such as in situ data. So this can come from whether it's citizen science or you have your in situ stations for your study area in here as well. And then you can get your time series and your plots to look at how those different data types compare. And finally, bring in other data types such as currents or any other data type that's spatially distributed into here. So the idea is that you then have it's not just Earth observation data necessarily, and this gives you then a whole other level of making better informed decisions. So it's a form of it's a delivery platform and visualization with the option to also process the water quality information in near real time. So that was a really fast run through. I'm fully aware of this. So I'll just summarize with two final slides. What I've tried to convey about, from our perspective in industry, the status of water quality monitoring is that there are a range of applications that we come across clients asking for. So whether it's environmental health monitoring, compliance, dredging is a big one. It's sensor agnostic because it's physics based, and we've already heard that mentioned in the other talks. In situ data perhaps is not really needed. The acceptance is ever increasing, and that's both for industry and government, which has been a nice journey to be part of. From our perspective, it's been extensively validated by third parties. We've had internally, at least as a company, operational systems running for more than 5 years now. In fact, we've had operational systems at receiving stations, ground stations for many years as well. But recently, we've now been able to offer turnkey software so that agencies can set up their own capabilities customized for how they wish to work with water quality data. So where do I see developments and potential from our industry perspective? Well, if you've described this radiative transfer problem with good physics, fully physics-based, then, well, physics is physics. So I see incremental improvements here perhaps, but no big step changes in where we can take water quality with Earth observation water quality. New sensors, Arnold has talked about this. Speaking from, I guess, from the coalface of users in the industry who want water quality data for some application, the main challenge or the main thing that we get asked about or that we come up against is actually temporal resolution, because a location can be cloudy, and yeah, they want a certain type of frequency in their monitoring. So that's actually the main bottleneck for us. It wouldn't be necessarily spectral resolution. We don't, for example, often get asked about different species of chlorophyll. We get asked about chlorophyll at the moment. And we are aware of the trade-offs, of course, of spectral versus spatial, which Arnold alluded to as well. We find that Sentinel at 10 meter spatial resolution, especially being free, has a lot of happy users. So that's just putting that out there. We don't often do coarser water quality monitoring for inland and coastal, especially not inland. So what are developments and potential? Regional calibration and validation. So this has been talked about in the previous talks, so biooptical databases and so on, in situ stations, field work. There will always be improvements if you can incorporate that in a virtuous cycle in your Earth observation of water quality monitoring. There will always be improvements, and that's important to note. I would put in there that it should be fit for purpose. So depending on what you're trying to achieve, there's probably a diminishing returns at some point. Citizen science has been talked about, and then online delivery platforms that I think incorporating more and more data types will, so assimilation essentially, really has potential to take this to the next level. And finally, so speaking from perspective at EOMAP, we're never going to set up field stations, say, throughout Australia to validate or calibrate our water quality products. And we're probably never going to invest in IT. Hello? We're not going to invest in IT infrastructure to be able to process all the data coming in for all of Australia, historically and near real time. So this is where national agencies play, to me, an obvious role, that they can provide this type of infrastructure and research. So on that topic, this is my last slide. From our experience setting up operational systems and and having worked in industry for many years now, some considerations for a national scale type operational water quality monitoring system using Earth observation data. The initial points here are probably pretty obvious. They've been more or less alluded to already, but I will go through them anyway. You need an accurate and robust atmospheric correction. This needs to be, because of the low signal to noise for aquatic applications, this is critical for the output of your data. Your algorithms, your system has to be underpinned by physics-based algorithms. This has also been clearly stated already. But what it can do is it can enable you to have this accuracy and error tracking, which I showed with the automated quality coding, and free you up from which sensor you want to use. And all these workflows need to be automated, and that includes the atmospheric correction and, let's say, the bulk of the QA/QC. Finally, near real-time processing and archive-friendly systems, so you can back process your archives. Those are all the considerations that we take into account in setting up these systems. When it comes to the delivery platforms, what we've learned is that although we like data and playing with it, a lot of clients aren't that interested. They want to be feel comfortable that the data is as accurate as it can be, but they might just be happy with visualization for everyday use. And finally, the validation and the CalVal efforts, the R&D around that with partner agencies, that's an ongoing thing, and it shouldn't be a bottleneck for setting up a system that you have to get everything right with full-fledged bioptical libraries before you start. That will always be ongoing. And so, so on that topic, from the private sector perspective, there may be some cost benefit or diminishing returns. You know, if you have a national CalVal system, how accurate do you need to try and be with your biooptical libraries for every location in Australia, versus if you want to have an analytics space industry where a local consultant is able to produce water quality information at high spatial resolution, do the water quality sampling, and really calibrate it and fine tune it to the client specifications for that location. So I think there is a diminishing returns there in how much CalVal you need to do for a national system. Keeping in mind, what I think is important, of course, is displacing the private sector Earth observation analytics in what you offer from the national perspective. So that's what I have to say. Thank you very much.
Thanks very much, Magnus. That covered a lot of critical points.
I know, sorry,
especially those last two slides. We do have time for questions. Initially, we'll take questions for Magnus's presentation. He raised a number of key points in terms of setting up and running these systems, some of which were in the flowchart that Janet and Steve had as well from a private industry perspective. So we'll just open the floor to questions there. I noticed Arnold's responded to some previous questions there, but any questions for Magnus there? I do have a couple, but I'll wait. Question from George Dykes, interested in knowing how much are customers really interested in calibration and validation, and I'd refine that in that, are they actually interested in calibration, or is it validation they want to know about?
Yep. When it comes to water quality, it's not often, I have to say. It would be for something like the dredging monitoring type work that we do, then they often have in situ stations anyway. And so they are very curious, especially if they're a first-time customer, they're very curious to compare. No one ever wants us to first calibrate our algorithms up front. You know, we provide them with a thick summary or compilation of case studies of what we can achieve, what they can expect. Yeah. They're usually very happy with that.
So it's more the validation side they're interested in.
Can happen, yeah. I would say that's maybe 20% of the time.
All right.
commercial work.
Just to follow on from George's question, the next one there is, he also asks, what might you get beyond Sentinel-2 from a dedicated satellite for water quality?
Beyond, well, it depends
Mm.
if you mean spatial resolution versus spectral, which I'm guessing is what you're after.
Mm-hmm.
Like I said, it's maybe a catch-22 there, that we rarely get asked for the kind of water quality information that would require a higher spectral resolution than what Sentinel-2 already has. So, but at the same time, maybe that's because that doesn't exist yet. So there is not, people don't realize that there might be more detailed information that could be achieved with higher resolution. But we never get asked for, usually, I would say 95% of the time, it's turbidity or suspended sediment. And we don't see a limit there on the spectral. On the spatial, again, even if there was free satellite data with a higher spatial resolution, I'm not sure clients would opt for that either, because it's a higher cost. It's, 2 meter data is 25 times more, is it? Pixels to process. That adds to the cost. So it wouldn't be a game changer for our business. I would say maybe, 10, 20% of our projects might use something higher.
But a higher temporal resolution repeat
That
would be...
That would be the one. That's what I mentioned. Yeah, thanks, Stuart. That would make a difference, because clients, they might want daily, or they might want daily, and you get a week with clouds, and of course that doesn't really help if you have higher spatial resolution. But higher temporal would definitely, they would spend more money if they could get more imagery. Yeah.
And just before we get to Manish's question, so Magnus, in terms of clients, for whether it's turbidity or other parameters, do they say, look, I want Sentinel-2, or it's like, I want a turbidity product at this level?
Yeah, they'll say, we need to monitor, we have dredging, we need to monitor that somehow. What can you offer? We will say turbidity or suspended sediment. And then it'll be a question of, how long is the dredging window, and how many images do they want in that period?
Yeah.
And then from that, usually they'll want 10 meter Sentinel data, because anything else is not going to tell them if it's turbid near the dredger or not. That's it.
All right. That sort of leads into what we'll call the last question from Manish. So Magnus, as you mentioned, a sensor agnostic approach is used. How do you plan to accommodate future hypersatellite missions like EOMAP?
Yep. Well, I'm not going to say trivial, but provided EOMAP has a nice spectral response function and they can provide it to us, and the signal to noise is good, it's fine. It's just another set of sensor parameters that goes into our sensor database, and it'll run. So essentially trivial.
All right, thanks, Magnus. Well, what we're going to do now is I just want to say a few words to wrap things up, and then lead into where we're going to be going on Thursday with the next part of the discussion. I'm just going to share my screen. Okay, right. So there's an outline of what we covered today. I do particularly want to thank Stephen and Janet and Arnold and Magnus for preparing their presentations and helping us build the structure on this. Hopefully that gave you an overview of what is going on at a number of different levels in government and industry, and also what we're looking at going through in the future as well. So today was an overview of what's happening. What we will move to on the second workshop on Thursday afternoon is, and it's actually at a slightly later time, sorry, the error there, is to look at, okay, how do you potentially move forward to build on sort of the strengths and gaps that we have. The end of Magnus's talk went through a number of those where it's clear there's some gaps and limitations. There are a few obvious areas where we've got complementarities between government and industry and having research groups in there. So Thursday is the aim is to explore all of those components and come out with directions in terms of how to go forward with that. There are some other questions that have come out after we finish the questions today, and I'll pass those on. I would just draw everyone's attention to a comment. If you look in the chat window that Larissa Marfan's posted, we do have a questionnaire up online at the moment, and that questionnaire, I'm just going to stop sharing this screen and show you another one. That questionnaire is helping us to obtain information in each of these different application areas. Some of you have already filled out the questionnaire. If you haven't already, we greatly appreciate you filling it out. We'll provide a summary of the identified responses on the EOGN website. So, please, if you are working in this area, we'd really appreciate you taking 10 plus minutes to go through this and type your responses in. Just showing you where the report and the survey and everything from EOGN activities ends up. This is the Earth Observation for Government Network page on the Earth Observation Australia website. Just tells you, what it's about. And then, we've got our previous workshops in there and the actual sessions themselves. And then there's also the reports which go along with them as well. And this information's used, it's used in our government agencies. We've used it in SmartSat CRC activities. The Space Agency uses it in some of its development activities. It's there for people to use, as a resource. So that's where we'll be going with that information when we actually do collect it. So just having a quick look through the other messages which are in there before we finish. No other key ones there. All right, so just noting that we've gotten to the end of today's session. Thanks everybody for your input. We'll be back online on Thursday afternoon at a slightly later time to talk through how do we potentially go forward and look at those complementary gaps between government, industry and research, and particularly how research in all those areas pushes things along. We will provide an update email in between today and Thursday. But again, thanks again to the presenters. Thanks everybody for participating, and particularly thanks to Larissa for setting up and running this. And we'll see everyone hopefully on Thursday afternoon. Thanks everyone.